All right. Quick thing. Okay, so read, pause. Correct answer is A. Whichever has less resistance, they have the same. They have the same voltage because of parallel. Next question, pause. Correct answer is C. Crazy cats. So we already established 1, 2, and 3. 4 is a combination of 3 and 2, and 5 is a combination of 4 and 1. Correct answer here is what happens. Nicely done. A, increases. Here's my analogy. Christmas time at Walmart. Okay. So you're the manager of Walmart. You're trying to get people in and out of Walmart as fast as possible. The resistance to that process is the checkout process, is the checkout lines. Okay, that's your resistor. If you open another checkout line, if you add another resistor in parallel, does that help or hinder the flow of people going out of Walmart? It helps. When you add another branch in parallel, there's another option for current to flow. Good with that? Tell your neighbor.
Isn't magnetic, but it would be current induced in it because of the magnet. It would heat up and kill you really fast.
That's true. That is true. Okay, correct answer is C, decreases. If the total current increases, the voltage isn't changing. Total resistance decreases. So as you add resistors in parallel, the total resistance decreases because you're adding more options. Oh dear. Tell your neighbor. Okay, correct answer is A. You can do the math if you'd like. Conceptually, here's the idea. Yep, remember to find the reciprocal. The equivalent or total resistance of a parallel circuit is less than the least resistor in a parallel circuit. Okay, I'll say that again. Okay, the combination, the equivalent resistance of a parallel circuit is less than the smallest resistor. You okay with that? Here's some other shortcuts for you. If you have and you have 12 ohms and 12 ohms, they're identical. This only works if they're identical. It's going to be half. The equivalent resistance is going to be 6. Okay, 1 over 12 plus 1 over 12 is 2 over 12. 1 over 6, 6. Good? Thanks, sir. If you have 3 that are identical, it's a third of that. 4 a fourth. This only works if it's identical. Good? Okay. Thumbs up when you have a guess. Have a conversation. Nice.
They shouldn't even like let. We're so good at what happens to the voltage when the resistor switches froze. If this is the entire ECS, we do that. This one cycle, like your entire.
Okay. Correct answer is? Okay. Yes, agreed. Increase. So you're going to combine these together in parallel. So, okay. So this is 2 and 3 is 1. When I can, okay, when a switch is open, you got resistance of whatever the R3 is. When you close this, this is parallel. This reduces that resistor. The resistance of that combined resistor. Okay, so the total resistance decreases. Voltage didn't change on the battery, so there's more current. So across this guy, that resistance didn't change. Total current went up. Voltage has to go up. Yes? Okay. Tell your neighbor. Is that premature? Yeah. Okay. Tell your neighbor.
No, you're right. It's no. Because the total current goes up. Yeah. So it feels like the current would. Well, if why would we're looking for whether or not the current goes up. Why would the current go down? It would. Yeah. So it can't be much. It's either A or C.
Oh, I see the dendrites firing.
Dangerous dinosaurs are
Okay. Oh, come on. Let me think. Okay, heard a lot. Here's what I heard. What are we looking for? Voltage across. Okay. Let's see. That's another good way. Okay. I heard all letters. Okay. So student A says it's the same because it's in parallel. Voltage is the same in parallel. Student B says no, the voltage increases because when that switch closes, the total current is more, and so you have more current. You didn't change the resistor, so the voltage is up. And another one says, well, no, I think it decreases because there's now more things to be fed. And student D says, I agree it decreases, but I think it's because there's less voltage to be given to the resistor 4. No, I'm just making up an AP question. Okay, because listen, they're not just going to give you increase, decrease, stay the same. They're going to give you a reason, and you have to not only know the answer, but why it's the answer. And whatever they give you, trust me, it's going to look tantalizing. Okay, correct answer is it's going to decrease because, okay, this is the exact same scenario as this. Okay, I mean, sort of. I just added a resistor. It's still parallel. The concept is still the same. The voltage across this guy, okay, here's the loop. We'll say 10 volts from the battery. This went from when I'm making these numbers up. You have 5 volts and 5 volts. Let's pretend they're identical just for kicks and giggles. Okay, when I close that switch, then this made this go to 6 volts. Right, increase. I don't know how much it, just making up a number. So this voltage gain equals voltage drop has to be equal to 4 volts. And that same conversation could be had with this one as well. There's no difference conceptually. You okay with that? Okay. Now, to address why the other people are wrong, student A was wrong because, oops. Okay, so let's, that's a bad example. Let's pretend, let's say they're not equal. Let's say we started with, it doesn't matter, 7 volts and 3 volts. There's 3 volts across this guy, 3 volts, okay? These two are the same. When I close this switch, that's going to increase that. I'm making up different numbers. This is going to decrease that to 2 volts. This is also 2 volts, and this will also be 2 volts. Those are the same relative to each other. Okay, because you changed the circuit. Okay, there is, some people said it was going to increase because now there's more current. Yes, there's more current going through this wire and through this resistor, but that it's only going, there's current going through this guy, current going through this, there's, the only thing that's effective is the current going through this total as it feeds and supplies current to this guy as well. Does that make sense? Yeah, good. I think does that make sense why those other people are wrong? Okay. Give that one a shot. Circuits made it be static.
Seth said he wanted to play good chess.
Oh, I think he'd beat me. It's been a long time.
Thursdays after school.
Okay. You don't play chess? I know how to play chess. I mean, I know how to play guitar, but you don't want me to play guitar. Like, it's...
beat your chest. Anybody gets 100 on the test.
No, I mean, that's like, that's like, what can we, that's like, until the curve, and then you're fine.
Just wait until my grade comes.
I have yet to have someone get an F.
Oh, really?
Yeah. Okay, have a conversation.
But then, this one's got but that one has the overall greater resistance is the same as so that has to be going on. Yeah, I think it's bro, I have no clue, but it just seemed right. Because they're all the same. Yeah, he should raise.
Correct answer is R5. Okay. This is a junction rule question. So let's just say, to keep numbers easy, there's 4 amps coming from the battery. When this hits, because they're equal resistances, they're split equally. You have 2 amps and 2 amps. They come back together, you have 4 amps going through this guy. That little, okay? And then here, because there's more resistance in this branch, we'll say 3 amps goes through here and 1 amp goes through this. Good? Oh, I like this question. Simon, did you want to?
Wait, you know, right?
Yeah. Every time Powell comes in here, that's the indicator that's.
I just keep it down.
Have a conversation. Tell your neighbor how you got there. Correct answer is 45 watts. Okay. So here we go. We know that there's 2 amps here. These are in parallel. 20 volts, 20 volts. Parallel, like a fun fact up parallel. So we know that this has 1 amp going through it. So we got 1 amp going here, 1 amp going here. That means there is 3 amps in here. Power, shortcut, I squared R, 9 times 5. Good. Okay, here's your original circuit. Okay, here's what we're going to do. What happens to the brightness of DE when BC is removed? So we had BC, we take that out. What happens to DE? Have a conversation. Tell why you think so.
Yeah.
Correct answer is rough. Okay. All right. So, so here, I'll just tell you. Nice. Okay, DE and GF are wired in parallel with BC. It is independently hooked up. The current nor the voltage will change across DE with that present or not. There'll be more current, there'll be less current coming out of the battery, true. But the current delivered to this will not change. The voltage, give some numbers, let's make numbers up. 10 volts across here, there'll be 10 volts across here, and 10 volts from here to here will be 10 volts. Regardless if this exists or not. Okay, same motivation, same pressure, same resistance, same current. Same brightness, independently hooked up. Okay, yes? There's more current coming, here, there's more current in this arrangement than in this. We decreased the current when we took out light bulb BC. Okay, through these wires here, less current. But right here, it splits. This would receive just as much as it did prior to BC being taken out versus being removed. Independently hooked up. I don't know if this is going to speak to you at all. Did Doc give you the water tower analogy? You guys mock it. That was my analogy. Don't mock it too bad. All right. So here, okay. So here's DE and GF. Here's BC. If I turn this off, that does not affect this. Independent. Good with that? Here's another way to draw a parallel. I'm wasting wires but conceptually, this is identical if the wires are perfect. Okay? Independently hooked up. You got a loop and you got another loop. You hear that? Like I'm trying to get you to go beyond just like, okay, if you say so. I want you to get to the point where you're like, oh yeah, that totally makes sense. I don't know why I thought the other way. That's what I'm going for. And I'm looking for that in your expressions. You're just like you're just drinking the Kool-Aid. Okay? You need to be like, oh yeah, what was I thinking? Half the test, right? You want to take a third, like, do you have, how long do you have? Like 7 and 8? Okay. So you've done this to the backside. Oh, and I'm going to put you.
Oh, you want me to look at the circuits?
Yeah. Yes, you do. Okay, next question. Yeah.
So why wouldn't the current, like if you're using the water tower, like why wouldn't the other side
Yes.
like start having more?
Good question. So the pressure is identical. The pressure is determined by the depth only. Okay, so you are draining the water tower faster with both of them open. You shut that off, it doesn't drain it as quickly, but the depth is the pressure, the motivation for this to go in and out is the same. Not in and out. The pressure for this to flow out didn't change. Like we have water towers in our cities because it doesn't change the pressure. If you live out in the country and you're on a well, you have a pressure tank, if you flush the toilet, that does mass chaos to like when someone's taking a shower. But if you're in the city, that's a relatively constant pressure, regardless if someone else in the house or in neighboring houses are using it. The pressure is the same, regardless of how many spigots we open here. I don't know if that speaks to you at all.
So on the last questions, was it just the presence of the other resistor in series that made the current change? Like when you had the switch?
Okay, so good question. So this is a different circuit completely than this. So this is the base unit or the base. So like if I simplify this, I'm going to simplify it to this. This is BC, and I'm going to lump these two together. This is DEGF. Does that make sense? They're parallel. This other one, the base was a series. I'm going to simplify these down in parallel, but then R1 is in series with 2, 3, and 4. How are we doing with that? Like the foundation of this one is series. The foundation of this one is parallel. Okay? All right. So, what happens to the brightness of FG when I short circuit? Okay, so let me just talk about short circuits momentarily. Okay? In an ideal world, this is just another thing in parallel, and this wouldn't change it. But reality is, this has so little resistance that the power supply can't provide enough electrons for it to go through this and a whole bunch through this. So what this does is it turns this light bulb off or makes it exceedingly dim so it doesn't even shine very, like there's a little bit eking through, but most of it's going this. You've heard the saying electricity takes the path of least resistance. I hate that because that leads to misconceptions, but it works well when you short circuit something. Short circuit means you have a circuit that's complete that doesn't have much resistance. So you have a whole, is that, you okay with that? Okay. If that messes with you, just pretend like I replaced DE with a wire. That's essentially the same effect. Okay. So like still a complete circuit.
There's no, huh?
Yeah, because current increase, same as.
Oh, the speed is a single one.
So usually it's.
Okay. So it'd be double.
Correct answer is, I got a vote for A, I got 2 votes for A. A is correct. It gets brighter. There is less resistance in this branch because these are in series. Has the same voltage. The voltage did not change. It's the same as the battery. You have this loop. Okay, voltage gain equals voltage drop. You have a 10 volt gain, no volts drop. All of that goes across that resistor. Gets brighter. Good? Okay. What happens? What happens to BC? What happens to BC when I have that short circuit? Have a conversation.
The resistance on that part.
Correct answer is? Correct answer is C. Stays the same. This is independently hooked up. Does not matter what happens in this branch. This loop, voltage gain equals voltage drop, did not change. 10 volt gain, 10 volt drop. Good? Okay. The total current coming from the battery increased, but that did not affect how much current was going through this guy. Okay. Short circuit GF, FG. Tell your neighbor. Everybody go see. That's just make sure we're learning something. Okay, it's the exact same thing when you short circuit DE. All right, Here's your original circuit. Okay, different original circuit. Okay. What happens to DE when I short circuit BC? Just think. Just give people a chance to think. Have a conversation. Correct answer is A. It gets brighter. Okay. BC is in series with FG and DE. If I get rid of this, that's going to decrease the resistance, the total resistance, because this is in series. If I look at the original circuit, voltage gain equals voltage drop, assuming that they're equal. You have 5 volt gain, a 5 volt gain. Sorry, 5 volt drop, 5 volt drop. Bring it back to 10. If I get rid of that, that makes that a 10 volt drop. Good with that? Okay. What happens compared to the original circuit? What happens to BC when I remove DE? No, it's broken. It is broken. Not a short circuit. There's been a switch that has been opened. Have a conversation. Okay. Okay, here's a coaching opportunity. When you're explaining stuff, stay away from it or they. Be specific with what objects or measurements you are referring to. Like an AP grader, they will light you up. Like it increased because this is because it is in parallel, and this is like you need to be specific. If there's any vagity, any ambiguity to like what this is, like no points. Like they zero in on BSing. Does that make sense? Even if you know what you're talking about and you said it and you don't specify that, you're like setting yourself up.
Yeah. Is that all it does?
Correct answer is it does get dimmer. Okay, so FDE and FG are in parallel. Oh, good catch. Nice, FN. DE and FG are in parallel. BC will get dimmer because DE, when we get rid of DE, that increases. So if I was to simplify the circuit, it would be BC and then D, E, F, G. If I take away DE, that takes a branch of parallel. This, when there's a junction and current has a choice, that screams parallel. Okay? When I get rid of this, I just got rid of a checkout line at Walmart. I increased the resistance, therefore the total resistance increased, the total current goes down. Okay? What happens to DE? Last question. When I remove this. Sorry, what happens to FG, the brightness of FG? Have a conversation.
Wait, does the voltage drop stay the same though? Or is the
Correct answer is correct answer is A. Gets brighter. This is the exact same question as this. Exactly the same concept. Okay, you got to do the loop rule. Okay, so here we just said the total current decreased. The resistance across this guy stayed the same. Current decreased, so voltage drop decreased. If this is 10 volts, it went from, I'm making this up, from 4, and this was 6. This now goes to 3. Now this has to become 7. Gets brighter. So, I don't know if this is an encouragement, but when I was teaching honors, I did this lab, gave a lab quiz. I don't know if you guys had this lab last year, but the lab quiz was like, ugh. Okay, same exact questions. Okay, you gotta watch the loop rule. Okay, that's what I want you to walk away from. Gotta look at the loop rule. That is foundational. More than Ohm's law.
So, looking for the power,
Yeah.
like what would happen to the current? Because the current would decrease as well. Right.
Yes. Okay. Good call. So, what we're going to look at is, so the resistance didn't change. Ooh, that's a tough. Let's see. What can I argue?
Because it made sense on the other one. Like
Yeah.
before, but now I'm thinking about it now, I can't.
Yeah. I mean, here's. I'll play devil's advocate for myself. Here's the thing I was going to show you. Like, hey, the voltage increased.
Voltage matters more.
But then you could, and this is where I don't know if I should tell you this, but then my brain went, well what about that? Shoot. So, oh, I need to stop recording that.